Here, use the microphone.
Quick announcement. So homework 1 is due tonight at midnight. Hopefully you guys are wrapping up. And yeah, so if there's any other questions, any last logistical questions or quick questions I can answer, we can pass around this microphone. If not, I will say that homework 2 will be posted sometime this evening, so keep an eye out on Piazza for that announcement. And yeah, okay.
So welcome back, everybody, to part 2 of Sources of Parallelism and Locality. And so today I'm going to spend about half the time finishing the topic from before, and then we're going to talk to a different topic and talk more about communication avoiding algorithms and what our optimality goals are, not just for linear algebra, but for anything that looks like nested loops. So just to give a recap of the last lecture, and questions are welcome. There were 4 kinds of simulations that we care about finding parallelism and locality in. We talked about discrete events, game of life, circuit simulation at that level, particle systems, which is what homework 2 is about to a large extent, systems of ordinary differential equations, and also maybe some algebraic equations, so simulating circuits and bridges falling down. And today is going to be about PDEs. And it's going to illustrate several of the same underlying problems that we need to solve. There's sparse linear algebra and all those kinds of things. But there's also going to be some new work, which is some new patterns, which is on structured grids and unstructured grids. And last time I mentioned there were these 7 patterns, 7 dwarfs that came up over and over again in all sorts of different simulation problems and in parallelism in general. And so today we'll concentrate on the 2 that we didn't do last time, which is structured meshes and unstructured meshes. So the problems that they all have in common, we talked about load balancing last time, which obviously to keep all the processors busy, you have to worry about that. And we illustrated that we had both static cases where we could maybe do graph partitioning on a fixed set of work that you had to do and lay it out over processors, or it might be dynamic. As processors collect in one location, you might have to rebalance them, and we had oct trees and quad trees to deal with that. The other reason we have to be careful about partitioning is to make locality, so that particles that need to communicate a lot with one another to figure out how they move around, for example, all get placed on the same processor, and we turn that also into a graph partitioning problem to minimize communication. And I also illustrated there can be a tension between these 2 things, because if all the work is happening in one small part of it, let's say a big circuit, it's natural that you'd want to spread that part of the circuit out across all the processors, but that might maximize communication during that period of time, because all the parts of the circuit are communicating with one another very rapidly, so there's lots of trade-offs. So let's go on to PDEs. And there are 3 different kinds of PDEs, and there are 3 different ways to parallelize them. And so I'm going to pick one as an example, but let me talk about all of them briefly just to remind you what they are. There's elliptic, hyperbolic, and parabolic. So elliptic is something where you want to compute gravitational potential or electrostatic potential everywhere in some space, so it's a steady state thing, nothing depends on time. What makes it challenging is there's global dependence. The gravitational potential at any point depends on everything else, so that's what's going to make the parallelization challenging. Hyperbolic problems, that means the wave equation. So things are propagating at a finite speed, the speed of sound, the speed of an earthquake, whatever that is. And so that means you only have local dependence because things move at a finite rate. And so there you're really only talking to your nearest neighbors every time step when you're parallelizing, so that's going to be easier to do. And then parabolic combines both of those. It's both time dependent, and at every time step, everybody depends on everybody. So it kind of violates relativity, but this is the model of physics that people have used for centuries to model how heat propagates, for example, or how diffusion works. So at every time step, you need to know what's the new temperature at that point, and you need to know the temperature at the previous time step, but it depends on everybody. So we're going to have both global dependence and local dependence to deal with. And the global dependence means we're either going to have a lot of communication or take super tiny time steps. So that's a problem, and so we're probably going to go with global dependence. And of course, real physics problems often combine all sorts of these basic ones. So if you're doing fluid flow, solving Navier-Stokes, you have a combination of all of these different things going on. And the same thing for elasticity. So for today, I'm going to pick a very simple model problem where I can state all the physics from, just based on your intuition, fits on one slide. And Fourier wrote this down centuries ago. So I have an iron bar, and it's red hot at one end, and it's ice cold blue at the other end. And I want to figure out how the temperature changes as a function of time. And so the temperature is going to be U. It's going to be a function of x, which is going to vary from 0 to 1 along the bar, and it's going to be a function of time. And I want to know how it changes. And so here's what Fourier observed in the laboratory centuries ago. So how fast is the temperature going to change at this point x at any particular time? Well, it's going to depend on the temperature at the nearest neighbors. So here's two situations. Suppose the temperature here is 0, -1 to the left, and +1 to the right. It's not going to want to change, right? Because it's at the equilibrium. It's at the average of its neighbors. So how do I capture that? I'm going to take the difference in temperature there, the difference in temperature there, and subtract. And if they're the same, I'm in equilibrium. It's not going to change. So this is what I'm doing here. I'm taking the difference in temperatures, or the slope, on this side, and I'm subtracting. So what if the temperature is +1, 0, +1? So I'm colder in the middle. It's going to want to go up. It's going to want to get warmer. So it's the same formula. I'll take +1 on this side and subtract -1 on that side, and that'll tell me I want to go up. So now, this is a laboratory observation, and now I just let h go to 0, and this converges to the second derivative of u with respect to x. So that's the heat equation, and that's what we need to solve. So let me just repeat that at the top there. There's the heat equation. And I should say C is the conductivity, so it depends on the material. And so just as I did with ODEs, I'm going to discretize time, but I'm also going to discretize space. So I don't want to compute this at every time step or at every point in space. I just want to do it at some discrete points. And I'm going to use, for starters, the exact same formula I did last time, which we called forward Euler. So I'll know the temperature at time t, and then I'll just take a linear step to get to time t plus delta. So I need to approximate this. It's exactly the same formula as in the last slide. I'm not going to change that at all. So there's the slope to my right, and I'll subtract that from the slope to my left, divide by h, and there's the change with respect to time. And so now let me simplify this a little bit, because u of xt appears twice. So this is twice my own value minus twice my own value plus my neighbor to my right plus my neighbor to my left. And I want to solve for the temperature at time t plus delta, assuming I know the temperature at time t. And that's very easy, because the temperature at time t plus delta appears once, so I get this nice explicit formula. So if I know the temperature everywhere at time t, I can just take a linear combination and get the temperature at time t plus delta. That's going to be a sparse matrix vector multiply, no surprise. Now let me simplify this a little bit by pulling out that constant, because that constant appears everywhere. So the conductivity times the time the time step divided by the space step. And that's what that formula turns into. So it's 1 minus 2z times my value plus z times my neighbor to my left and my neighbor to my right. Now, as I said, I don't want to do this for every value of time and space. I only want to do it at space h, 2h, 3h, where h is some spacing. And I only want to do it at time steps delta, 2 delta, 3 delta. So instead of this function, I'm just going to have an array. And I'm going to compute the value in the array. And so there it is. So if I know the temperature at time I, then I just take these linear combinations to get the temperature at I plus 1. So this is a very simple model, and we'll see how well it works. So this is called finite differences, and so this is just repeating the notation from previous slide. So U sub ji is the temperature at time I times delta and j times h. And so here's the array of I and j values. So I know the initial temperature, that's at the bottom, and I know that this end, the temperature, this end of the iron bar, it's hot. This end of the iron bar, maybe it's cold, and I want to know how it changes. So at every time step, I'm going to average 3 nearest neighbors, my own value, left and right, and take some linear combination and get my new value. And this corresponds to a matrix vector multiply by a very special matrix T, which is very simple. It appears over and over again in science, and I'll write it down on the next slide. So there's the formula. So to get to time step I plus 1, I take those 3 combinations, and so that is a matrix vector multiply. This is the column vector of all the temperatures at time I to time I plus 1, and there is the matrix I want to multiply by. So z times my neighbor to the left, z times my neighbor to the right, and 1 minus 2z times my own value. So let me simplify this a little bit. I'll pull the 1 out of the diagonal. That gives me the identity matrix. Everybody else has a factor of z in it, so I'll pull z out, and I'm left with this constant matrix, which I'm calling L for Laplacian, another famous mathematician. So it's very simple. 2's down the diagonal, minus 1's off, and since this matrix is so simple, we obviously don't have to store it explicitly. I don't have to store lots of 2's and lots of minus 1's. I just have to remember this very simple pattern. And this very simple pattern is called a stencil. And I'm going to write it down by saying, here's my iron bar, or my domain. I'm discretizing it at all these red points. And at every point, I do exactly the same operation, because every row is exactly the same. It's 1 minus 2z times my value, plus z times my left neighbor, plus z times my right neighbor. So this is a very simple thing. To do that matrix vector multiply, this is all 1D. We're going to make it harder in a moment. And for a 2-dimensional mesh, of course, I don't want to just average with my left and right neighbors. I'm going to have neighbors above me and neighbors below me. And we'll do that in a moment. But so let's talk about how to parallelize this before we get to the higher dimensional case. So it's sparse matrix vector multiply. We taught by that very simple tridiagonal matrix. We talked about how to do that last time. And in this case, it's so simple we don't need to run any algorithm. Your intuition is perfectly fine. So how do I break this up into p chunks, where p is the number of processors, so each processor gets an equal amount of work to do and communicates as little as possible? Well, if I have 12 points on my mesh and 4 processors, everybody gets 3 consecutive points. Most of the work is just talking to your nearest neighbor, and there's exactly 1 wire connecting you to each neighbor, and 1 word has to travel along that to evaluate it. So this is obviously as good as you can get. And later, we're going to have much more general sparse matrices and run graph partitioning algorithms and so forth. So this is exactly how you would solve the wave equation. I mean, you'd have different weightings and so forth, but it's the same idea, average with your neighbors. But this has a problem with the heat equation. So let me just show you what can go wrong if we do this. So the answer can blow up. That's the problem with this. So it turns out that to get the right answer, this constant z, which depends on the conductivity, the time step, and the space step, has to be less than a half in order for this to work. The solution will blow up, and I'll show you a picture on the next slide if it gets too big. So why is this a problem? Well, suppose that I want to have a finer resolution. I want to know the temperature at more space points. So I make my space distance 10 times smaller. That means I have to make my time step 100 times smaller in order to get the right answer. And that's just not going to scale very well. So let me just do a simple simulation and show you what happens. So up here on the top, I'm going to take that number z equal to 0.42, so I should get the right answer. So here I have a plot where the iron bar goes from left to right, and the temperature is in the vertical axis, so it's hot in the middle and it's ice cold in the ends. And time is the axis coming out of the board. And as I simulate, no surprise, it keeps getting colder and colder and finally converges to the temperature at the ends. Now, if I take that constant and raise it from 0.42 to 0.58, it starts cooling off as expected, but eventually it blows up. And it's going to blow up exponentially, and that's just the nature of the mathematics, and and that's going to happen for any explicit method, where I take a forward time step by some matrix vector multiply. So I'm going to have to do the same trick here that I did for ODEs. I'm not going to use forward Euler. I'm going to use backward Euler. So that means I'm going to have to solve a system of equations at every time step, not just do a sparse matrix vector multiply. And so the only difference to derive this is, so there's this is the same as the previous equation for forward Euler. It's just the time derivative. And all I do on this side is I change the second derivative. Instead of having at t, I have it at t plus delta. So it's at the other end of the time step. So this is what I need to solve at every time step to get from time t to t plus delta. And if I rearrange this, I see that I know that all the temperatures at time t, but now I have this linear combination of stuff that depends on the unknowns at time t plus delta. So I have a system of linear equations to solve. So let me simplify it again by changing this, using that variable z. And I only want to do this at discrete times, delta, 2 delta, 3 delta, and discrete space steps, h, 2h, and 3h. So I get this array. And when I write down the system of linear equations, it looks almost the same as it did before. I still have that L matrix, the Laplacian. But now I have this tridiagonal matrix times my vector of unknowns equals what I know at time t. To get to time t plus delta, I have to solve a system of equations. And so it's the same Laplacian as before. So at every step, I have to solve this very simple tridiagonal system of linear equations. And this is not hard to do if you're just solving a one-dimensional problem. If you run this sequentially, it just costs order n time to do it. So it's not a big deal. It's going to get hard and interesting when I have 2 dimensions and 3 dimensions. So in case there's an expert in the audience, let me just say how things really work. So this is from the previous slide. I have to solve the system of linear equations at every step. But if you're an expert, you might say, hey, wait a second, there's something better than either of those. It's called the trapezoidal rule. And in that case, I do a matrix vector multiply, and then I solve a tridiagonal system. So it combines, sort of takes half a forward step and half a backward step. And so I still have to do a sparse matrix vector multiply. The matrix is just a little bit different. And I still have to solve a system, and the matrix is a little bit different, so all the problems combine. So even if I use the right algorithm. So again, I is the identity, and L is this tridiagonal. And so this is the heat equation. And let me say that if I'm doing a Poisson equation, so elliptic problems instead of parabolic problems, I still need to solve with the Laplacian there. So I still am going to be solving systems of equations with this matrix. It's just going to be slightly different in form. Okay, so this is all one more slide, and then we're done with physics, and we're just going to do computer science again. Okay, so I just want to tell you a little bit more about why the Laplacian shows up, where we get Poisson's equation. So it comes up in many places, and the easiest one to understand is gravity. So we know that if you have a particle at that point x, y, z, and there's a particle at 0, they attract one another. And what's the force? It's an inverse square law. So the force on this particle is going to pull it toward the origin, and the length is 1 over r squared. Okay, so that's the inverse square law. So we want to compute that, but we don't want to compute forces. It turns out it's easier to compute a scalar instead of a vector, and that scalar is called the potential. And that's just 1 over r, minus 1 over r. And the reason we do that is that if you know that, you can just take its gradient, and it'll give you the force. And so the good news is that this gradient satisfies Poisson's equation. So that's what we need to solve over and over again for lots of different examples, be it gravity or electrostatics or fluid flow or you name it. Okay, so I'm done with physics. And so now I've told you all about the one-dimensional problem. And so now I want to talk about what gets interesting and harder with higher dimensional problems. So now, what happens to this equation when I have a two-dimensional space? So now, instead of having a one-dimensional iron bar, I have a square. And I know the temperature on the boundary, and I want to know the temperature inside. That's the simplest thing. So at every one of these mesh points, I want to know the temperature. And so the formula is not just averaging with my neighbors to my left and my right. I have to average with my neighbors above me and below me. And so it's going to be 4 times my own value, minus my neighbor to my left, minus my neighbor to my right. But now, where do these other minus ones appear? So I have to decide how to number the points in this mesh. So I'm just going to number them left to right, 1, 2, 3, 4, 5, 6, and so forth. So these are going to be a distance 3 away. So that's my neighbor above me, and that's my neighbor below me. And if this were an n by n grid, this would be n away and that would be n away. So it would be a much, much wider band. So now, if I were just to do sort of an obvious, algorithm, which I'll tell you about, it would be much slower than necessary. So let me give you kind of a tour of what algorithms there are by talking about a typical office hours that I have. So And so this sort of, I'm going to walk through this by saying this is an office hours conversation. The student comes in my office and they say, I need to solve AX equal B. What should I do? And I say, well, why don't you just try dense Gaussian elimination, dense LU. There's lots of great software out there in parallel. And you can just call it, and it runs in n cubed time. And they say, well, that's not fast enough. And then I say, well, tell me some more about your problem. And then they say, well, actually, my matrix has a lot of zeros in it. And if you look up in this corner and that corner, it's all 0. And then we talk a little bit more about how wide this band is. And I finally say, oh, you have a band matrix. There's a band Gaussian elimination that exploits all those zeros. And in your case, the cost is going to go down from n cubed to n squared. You must be happy now. And they say, no, it's not fast enough yet. And I say, well, tell me some more about your problem. And then the student says, well, I actually know more about my matrix. It's symmetric. And in fact, I can tell you what its largest eigenvalue is and its smallest eigenvalue. They're both real. And in fact, it has a lot more zeros in it. If you look at any row, there are only 5 non-zeros. So we talk about that a little more, about what the largest and smallest eigenvalues are, and say, oh, great, you can use an algorithm called conjugate gradients. You only need to do sparse matrix vector multiply at every step, and your complexity has gone down from n squared to n to the 3 halves. You must be happy now. And the student says, no, it's still not fast enough. And then I say, what problem are you really trying to solve? And then they say, well, I know the temperature. I have this square, and I know the temperature on the boundary, and I'd like to know the temperature everywhere inside. And I say, oh, you're solving Poisson's equation. Why didn't you tell me that? You should either use the fast Fourier transform. That'll give you a complexity of n log n, or an algorithm called multigrid, which is n. And n is the lower bound. You have to do at least n work to get an answer of size n. So this typical office hours is actually captured online in various decision trees. So this went through a sequence of questions. The sequence of questions about the properties of the matrix could have gone many different directions. And so we've captured all this in a table, in a tree, which points you to different algorithms and different software. And so here's a lot of other algorithms that appear in that tree. And these are all sorted in 2 ways. They're sorted both in how fast they run on Poisson's equation. And I should say there's both the complexity when it's a 2D Poisson, and sometimes it's a little bit different when it's 3D, so that's in red. And it's also sorted by, in some sense, how restricted, how many assumptions you're making about your problem. The more you know about the structure of your problem, the closer you can get to the lower bound. So that's the serial case. So the rest of the columns talk a little bit more about parallelism or potential parallelism. So a PRAM is a magical parallel machine, which is just useful for thinking about parallel algorithms. Basically, communication is free. We know that's not true. You can have as many processors you want and as much memory as you want. It's just sort of thinking about parallel algorithms. And so you can see that you can go from n down to log n to solve that problem, assuming, and this is how much memory you need, and this is how many processors you need. So later in the semester, we're going to explore these, some of these in a little bit more detail and how they work, just a few of them. Certainly we'll have a whole lecture on the fast Fourier transform, for example, because that's used in so many things besides solving Poisson's equation. So here is a little bit more detail about office hours. You can read if you like. OK, so how do you choose one of those algorithms? Because many of them work. And so here's some very old data from 1991 on a 1,000 processor machine. But it's still, the relative values here still illustrate what's going on. So here are 3 rows of that table. An n squared algorithm. Where's my... There we go, an n squared algorithm, an n to the 3 halves algorithm, and an order n algorithm. Now, in homework 1, your goal is to do as many floating point operations per second as possible. And here, the order n squared algorithm is doing 1,800 megaflops. You can tell how old this computer is. Your laptop's much faster today, but it's on 1,000 processors. And multigrid is only running at 300 megaflops, so much, much slower. But if you look at the time, multigrid is doing 300 times faster because it's only doing order n operations instead of order n squared. So sometimes these fast algorithms are running more slowly, but they're doing so many fewer operations that they're obviously the right ones to choose. But in your particular problem, you'll have a trade-off, right? So it's not clear which one will always win. Here, the winner is obvious. OK. So to summarize all of these, the stuff we've talked about so far, as with ordinary differential equations, we have both explicit methods, sparse matrix vector multiply, or implicit methods where we have to solve a sparse system of equation at each step. In the solving case, there's two approaches. There's direct methods, so variations on Gaussian elimination, or the FFT is a direct method. And those are interesting and harder to parallelize. We'll have another lecture on that later. And then there's iterative methods. So multigrid, the winner there, was an iterative method. Its core is still doing sparse matrix vector multiply, which we'll talk about more later. And so we have all these graph partitioning issues to solve. Now, I only showed you 2D meshes and 3D meshes, and there, how you lay things out is, very easy. You just divide things into squares and cubes that we talked about before. But it turns out to be much more interesting. Real practical meshes are not so simple. So what I'd like to give you now is a visual tour of what other kinds of meshes come up besides the simplest ones and what extra challenges they have. So everything I've said about 1D, 2D, and 3D meshes is important because those are building blocks for more realistic looking grids. But practical meshes are often irregular, and I'm going to show you 3 varieties. One is, I'm going to call them composite meshes, where you take a bunch of regular ones and sort of stitch them together at the edges to build some larger, more complicated thing. The other one is unstructured meshes, which could come from doing a finite element model or a CT scan of some arbitrary complicated thing, and the geometry is whatever it is. But you still have to solve all the same problems. And then the most challenging of all are adaptive meshes, where it's changing from time step to time step. And there the typical example is you're trying to, for example, follow a flame front. And so all the detail is right at the edge between the burnt and the unburnt material, and you need a really, really fine mesh right there. And it's moving, quickly probably. And so you have to adjust your mesh as you go along. So let me give you some tours about what this looks like. So here's a composite mesh, kind of just a toy example. So you could think of this as a slice through a bridge abutment. So each of these subparts is a nice regular mesh. So to think of this, each point, each vertex in this graph represents a row of a matrix. So that could be row 1 and that's row 2. And if you see an edge connecting 2 points, that means there's a non-zero there. So this means A sub 1, 2 is non-zero and so forth. So the question is so this is, represents some geometric composition. These parts are simple to understand, but they're all connected in different ways. So let me show you what it looks like when you actually build the matrix that this involves. And so to do that, I have to choose some numbering. So here, this regular mesh, this is a 7 by 7 mesh, so that's going to be the first 49 nodes. The next one, from 50 to 91 is another regular mesh, and so on going around. And here's what the matrix looks like, corresponding to all the non-zeros. So these first 49 non-zeros correspond to these first 49 band matrix. So this is kind of like the 2D Poisson equation. So it's just sitting up there. These next blue ones correspond to that blue part. That pink one corresponds to that. But I have all these other edges because they're connected. So these green nodes are connected to the red nodes, and those correspond to all those red dots out there, which is makes things more irregular. And these first 49 nodes are connected to nodes, numbered in the 300s, these blue ones. So I get some more connection out here, connecting those greens to those blues. So this is what my matrix looks like, and the question is, what is this going to cost me when I try to solve it? So let me just give you some examples in what the design space is going to look like if I actually try to solve this problem, a system of linear equations with this problem. And so what I'd like to do is use Gaussian elimination. Actually, this matrix is symmetric and positive definite, so the algorithm is called Koleski, but it's still basically Gaussian elimination. So here's the matrix I had in the previous slide, and now I'm just covering everything with little black dots represent the non-zeros. And I'm going to run Koleski on it, Gaussian elimination, and this is what the output is. So everywhere I had a non-zero here, I get a non-zero in my factor, my output. But the way Gaussian elimination works is I'm adding multiples of one row to the next row, and so I may get a lot of new non-zeros when I add a non-zero to a zero. And so all the reds are the new non-zeros that appear. And so here I went from having about 4,000 non-zeros to having about 12,000 non-zeros, which is going to complicate the data structures in all sorts of ways. And the total amount of work was about 300,000 floating point operations. So what kind of optimizations can I do here? So the answer is, not surprisingly, graph partitioning. But now what I'm going to use that for is to reorder the rows and columns. So this matrix and that matrix are the same matrices. They only differ by the order of the rows and the columns. And so why is this good? It's because if I now take this one and do the same Gaussian elimination algorithm, I get this, which has a lot fewer non-zeros, and it takes a lot less work. So instead of having 12,000 non-zeros, I have 8,000. Instead of doing 300,000 flops, I'm doing 200,000 flops. This is a tiny example. If I were taking a huge problem, this would go down by factors of tens, hundreds, thousands, the amount of work and space. So this was for a regular problem. Let's see what happens when I do an irregular problem. So if you have MATLAB on your laptop, you can just type load airfoil, and this will appear. So it's all sort of built in. And so this is a two-dimensional mesh around a wing and some fins. And you can see that the mesh is very much finer around the front, which is where you want to compute the turbulence. And so you need to resolve that very finely. And you also want to compute the turbulence around the fins. So this is the way the mesh will look. Here's the matrix, and with a good ordering. And so you can see almost all the non-zeros are near the diagonal, but there's lots of dust and connections out there. And when I run Cholesky on it, this is how much fill-in I get, which isn't too bad. Okay, so that's one place that irregular meshes can come from a finite element model of some thing that you want to model, but you can also create them yourself. And this actually happens quite regularly. So suppose that I want to solve a system of equations, and it's defined on this nice regular cylinder. Okay, so I mentioned this algorithm called multigrid. What am I going to do there? The basic idea is I want to take this nice regular cylinder and approximate it with a much smaller problem. Solve the smaller problem and use that as a starting guess. So how do I get a smaller problem? I'm going to take this mesh, throw away every other mesh point. And then if I throw away a mesh point that had connected two prior mesh points, like ones in between the others, I'll put an edge back in. So this is also a cylinder with half as many mesh points as before. And you can see it looks pretty much like the original cylinder. And so the idea is I'm going to solve this much smaller problem, about a quarter the size, get a starting guess, and use that to iterate on this one. Now, if that was a good idea, why not do it recursively? So I'm going to take this smaller problem and throw away every other mesh point and reconnect it and solve that smaller problem, et cetera, et cetera. And if I keep doing this, you can see eventually it stops looking like a very regular mesh. But it's still a good idea, but these become much more coarse as time goes on. So let me tell you one more example, which was actually a joint project with some colleagues in mechanical engineering, Panos Papadopoulos and Tony Kevney. So this is a bone from a cadaver from the spine, from a vertebrae. And so the motivation for this project was osteoporosis. So the idea is that older patients have a lot of weakening in their bones. They get less and less dense, and so they're in danger of breaking their backs when they fall down steps. So the question is, how do you predict that and treat them? So the standard diagnosis was you take a little sample of the bone and you say, what's the bone density? And if it's too low, below some threshold, you say, okay, you need help and we're going to do something about it. And above that, you say you're okay. That is not a very good predictor because there's a lot more complicated structure than density alone will do. So what Panos and Tony wanted to do was have a much more accurate prediction of the strength of this bone. So here's the experiment they did. They took that particular bone and they put it in a micro CT scanner and created an image of it at 22 micron resolution. So here is a subset of that bone, and in all the detail of where all the bone is and where all the air is. And you can see that there's a lot of air in that bone. Then they made a finite element model of this image, and it just not the whole cadaver, but 2.5 millimeter cube, and there were 44 micron size elements, and that led to a matrix of size 500 million. Okay. And they needed to solve that system of linear equations. And they did that using multigrid, and they won a Gordon Bell Prize. So Gordon Bell Prize is giving its supercomputer every year for sort of the biggest, most simulation that has been done on a supercomputer that hasn't been done before. And so now is this practical for a human being? You know, you can't take a bone out of a patient's back, and if you try, and this uses much too much radiation to try to do it while it's still in there. And so I think that Tony had a startup. I'm not sure what happened, but the idea was, can they do a lower resolution imaging and still do this kind of stuff and get as much accuracy as they got out of this one? I should say, so the way they validated this model is they took this bone and then they, and they put an amount of pressure on it that was predicted to break it from this. And it predicted the laboratory break point very accurately as to when it would fall down. So the idea was that you could use this to give much more accurate information to a patient on when they needed treatment. Okay, so that is an irregular mesh. And here's the last example, also a local one. So some folks at LBL do this kind of work, so Phil Colella, John Bell, and this is you trying to simulate a supernova. And so here is a picture, two-dimensional slice of a 3D simulation of a supernova. And so out here, the mesh is getting much, much finer as the face of the surface of the supernova expands. And of course, it's expanding rather rapidly. And they have to move the mesh out. And here's more of a three-dimensional picture once they get out. And that's what they're trying to do resolution on. And so what you need to do is very rapidly build these patches and move them around and rebalance it and run multi-grid at every step. So this has generated a lot of software. There's a lot of projects that work on this. In fact, a whole programming language called Titanium was invented here to make it easier to program these kind of applications. Phil has a widely used package called Chombo, which was developed at LBL. John Bell has another package. A colleague at UC San Diego has yet another package. So part of the lesson here is that you don't need to reinvent wheels. There are a lot of wheels that exist and that we'll have more detailed lectures on, but all these parallelism problems do come up. Okay. So just to summarize the challenges of these irregular meshes. So how do you generate them in the first place? You might start with a geometric description of an object, but then, which might come out of a CT scanner or something, but then you have to make a mesh out of it. How do you do that? That's an interesting computational geometry problem. And one of our colleagues, Jonathan Chuchuk, has a system in the 2D case which actually produces provably optimal meshes in the 2D case. 3D is harder, but there's software he has it for out there too. We talked about graph partitioning a lot, and there are a lot of packages people have built, and we'll have a lecture on those later. Parmetis is one. Now there are a lot more, so you don't have to implement all these graph partitioning algorithms. I've talked about all these iterative solvers, multi-grid, Jacobi, SOR. I had a whole slide of that. They are so often used that the Department of Energy has invested a lot of money in building packages where they're all implemented in high performance, so they're easy for you folks to use. So we'll have a lecture later on one of them called PETSI, but there are a lot of others. We worked on our own package, which I mentioned won the Gordon Bell Prize for the simulation of the person's back. And so these kind of ideas have now been incorporated in some of these other packages too. And then there are direct solvers, SuperLU, which are Gaussian elimination on sparse matrices that run in parallel. And SuperLU was invented here. It's maintained at LBL. And so there's lots of things available there too. But there's still various possible projects that all of these could lead to. So to summarize, all four different kinds of parallelism that we've talked about, simulation types. So we talked about how to identify parallelism in locality, in discrete events, particle systems, ODEs, and PDEs. And we identified 7 dwarfs. And I had these up there before. Today we saw how structured grids came up and unstructured grids. And the FFT came up because of its use in solving Poisson's equation. And dense linear algebra we talked about last time. We saw sparse linear algebra both yesterday and today, particle methods, and then Monte Carlo. And just to put up this picture that I had last time as well, the original 7 dwarfs were derived by looking at scientific applications, everything the Department of Energy did, and then a bunch of Berkeley colleagues got together and said, what about the rest of Silicon Valley? They looked at machine learning, games, databases, and so forth, and they found 6 more. And so today we have finished identifying the original 7 and where they come up, but we're also going to have lectures later in the semester about how do you parallelize, graph algorithms and things like that. And this heat plot plot says how important each of these kernels is in all of these different use areas that we looked at. So linear algebra comes up in lots of places. Others are a little bit more focused. Okay, so that's the end of sources of parallelism. And I think, so Ed, did you have, you gave your announcement about homework at the beginning, right? Yeah. Okay, so I'm now going to stop and move on to a different topic. So this is a good time for questions, if anybody has any. Yes, do we have a microphone for the questions? Yeah. Here, let me just make sure we capture your question. Yes, I think you're supposed to catch it. It's this blue box.
So the microphone's just for the recording. It's actually not being amplified right now, but I can relay your message.
Okay.
I just want to ask if our project must fit in one of those
No. Your project is totally free. So some folks who come from another department where they're trying to parallelize an application from some application area, might use existing software that's been developed, in one of these other in prior work to parallelize their application. Some folks may want to build their own low-level super fast version of one of these. Everything is possible, and we're going to have hints later on what projects are reasonable. And I think you already submitted a what your interests are, and we've posted that someplace, and hopefully that can help you build a team. But we have lots of pointers to previous projects that you can use for inspiration as well.
Cool, thank you.
Okay. Okay, so let's hope my laptop doesn't crash when I go to the next slides.
Any other questions?
Okay, so what I want to do now is say a little bit more about what communication optimal matrix multiply is, which was, of course, what your first homework was about, just on one processor, and then talk about how those ideas generalize way beyond, basically any code that looks like nested loops accessing arrays, which is a lot of different kinds of code. So just to remind you of the notation, when I say communication, I mean moving data. And that could either be between main memory and cache, or between cache level 1, cache level 2, all those different things, or between processors over a network, which is going to be the main emphasis in the rest of the semester. And this is the most expensive operation, as you've discovered by doing homework 1. And so what our goal is to come up with algorithms that provably minimize how much data they move. And so I'm going to start with a simple example, which is the n-body problem. And because there your geometric intuition is perfectly good enough to see what the optimal algorithm should be. Then I'll do it for matrix multiply, where it's a slightly higher dimensional intuition is required. And then I will sort of state a general theorem, but not prove it, that says that any nested loops, any number of arrays, any subscripts, we know what the lower bound is, and we know how to optimally tile it, find the right blocks. And I'll give you an example that we worked at recently on convolutional neural nets, which is obviously an interesting topic. And the interesting observation we made is you can, currently, how do people do it? They just change it to matrix multiply, and they call the BLAs. You can beat matrix multiply, in theory, by organizing it differently. Okay. So let me go on. So let me do the simple case where hopefully your intuition is enough to see what the right thing to do is. So I'm going to have an array of structures. So that may be the position of particle I, the charge on particle I, some data structure. And so here is the simplest way to write down the classical algorithm. I'm going to loop over all pairs of particles, I and j, and I'm going to compute some function which depends on particle I and particle j, and I'll compute the force and update the force in particle I. So in this function, I don't care what it is, just does some arithmetic. So I'm going to simplify this a couple of times so that we can make a very simple geometric model of what this is doing. And so let me have two sets of particles. So I'll have particles A and particles B. And I'm going to want to take all pairs and compute some scalar function. And so I don't need to update another vector. I'm just going to update some total potential that's living in a register. So just to keep it simple. As I said, the theory deals with anything, but I want to keep this simple. And now I really don't care what function I'm computing. That could be any arithmetic I want. So the simplest model is that I'm looping over all pairs of particles, I and j, and I access a sub I and access b sub j. That's all I need to know. And that will let me draw the following picture. So I can think of the algorithm as basically touching all of these points, these ij points, and doing something there. So for I equals 0 to n, j equals 0 to n, access a sub I. So let's suppose I want to just do that one point, so that's I equals 3, j equals 5. What data do I need to access that point? Well, I need a sub 3 and b sub 5. And geometrically, all I need to do is take that point and project it onto the j-axis. That tells me which entry of b that I need, and project it onto the i-axis. That tells me which entry of I that I need. So what if I want to do a whole bunch of work? So I want to do all those points. All I do is take their projections. So I need all these 4 different entries of A and all those 3 different entries of B, because these two share the same entries of B. So that's a very simple geometric model. So now, here's the optimization problem. So to keep it simple, let's suppose my cache is of size 10. And so I can only have 10 entries of A and B in fast memory at the same time. What's the largest number of iterations that I can do? So what this means is that when I do that projection, I can have a total of 10 dots on the I-axis and j-axis. How big, how many points can I have? So what's your intuition? So if I pick any number of points down here and up there, I can take all possible combinations. So I'm always going to get a rectangle. And the question is, what's the shape of the rectangle? And I know that I have a bound on the perimeter, and I want to know what's the maximum area of a rectangle. And your intuition should say it should be a square. So that tells me I can do at most 5 squared different things. And if I have a slightly larger cache of size m, the best that I can do is to have m over 2 entries of A, m over 2 entries of B, and I can do m squared over 4 loop iterations. OK, so this is all we need to know to write down a lower bound for any algorithm that solves the n-body problem. So here's the intuition. So there's the code again. So what I just showed was that with a cache of size m full of data, I can only do m squared over 4 loop iterations. So suppose I want to do n squared loop iterations, right? I want to run the whole algorithm. That means I need to refill my cache this many times, right? N squared divided by m squared over 4, that many times. How much does it cost to fill the cache? Well, the cache is of size m, so it's m reads and writes. So the total amount of reads and writes that I need to do is a number of the iterations, this quantity, times m, and that's 4n squared over m. Now, this, I've sort of swept some details under the rug here. I've counted a little sloppily, but that all it would change is that 4 would get a little smaller. But it's still n squared over m is the idea. Okay, and we have a formal proof, but this captures all the intuition of that proof. And so I'm going to write that lower bound as big omega, which means it's lower bounded by some constant multiple of the number of loop iterations divided by m. So no matter what I do, that's how much memory traffic that I absolutely have to have. So the question is, how do I attain that? What algorithm attains it? And I think that the picture that I drew you with the square is all we need to know. So what I need to do is read in some entries of A, some entries of B, and maximize the amount of work that I did. So if my cache is of size 10, I'll read in 5 entries of A, 5 entries of B, and do all those points. Then I'll go over there, read in, I can reuse these entries of B, and I'll read in those entries of A, and I can do that square. Then I can do that one, then I can do that one, and that obviously tiles, all the possible data points. It sort of fits nice and simply. And if you were to write code that did this, you would have 4 nested loops. You would loop over all of these squares, that one, that one, that one, that one, and then you would do another 2 nested loops to do all the points inside each square. So I hope this reminds you of homework 1. Okay. So now, many algorithms look like nested loops. And so let's use this same intuition and apply it to homework 1. And what does this tell us about MATML? So now I have 3 nested loops, and so here is going to be the proof, and so I'm going to have to, the two-dimensional intuition that squares are the best is going to get a little more complicated, but so let me just walk through it again. So it's going to be analogous to n-body. So let's suppose that in my cache I only have m entries of A, B, and C. What I need is an upper bound on the number of different loop iterations that I can perform. Before, it was the number of entries of A times the number of entries of B. It was m squared. Now it's going to be different. So what I need to do is have some magical upper bound on the number of loop iterations I can do, given a bound on how many entries of A, B, and C that I have. So, and let me call it upper bound capital F. That's going to be the math problem. Then that tells me I need to refill the cache n cubed over f times to finish the algorithm. And every time I fill up the cache, it's cost me m, so that is going to be the lower bound on how much memory traffic I have. I need an upper bound on the amount of work I can do, and for n-body it was n over 2 squared, and now it's going to be some other magic number that I need that's going to depend on the cache size. So what I need to do is, like n-body, I want to draw a picture, but now instead of it being 2-dimensional, it's going to be 3-dimensional because I have I, j, and k. So here is a 3-dimensional picture of the iteration space for multiplying 2 3x3 matrices, just to keep it small. So I have a cube, right? And it has an I-axis, a j-axis, and a k-axis. Every square on this face of the cube represents an entry of A, so that's A sub 1, 3, 1, 2, because this is the I-axis and the k-axis. And every cube represents an operation. So this cube here represents doing C11 equals C11 plus A13 times B31. So that cube represents a particular operation because it's ijk equals 1, 1, 3. What data does it need? Well, it needs that entry of A, that entry of C, and that entry of B. So it's the projections in those onto the 3 faces of the cube. In the n-body case, I projected on the I-axis and the j-axis. Here, I project onto the faces of the cube, but it's the same kind of geometry. So the question that I had is, if I'm only allowed to have m faces, m squares, m entries of A on this side, m on this side, and m on this side, how many cubes can I have? Okay. So to give you some intuition, here's the picture again. Here's my ijk cube. And let's suppose that I want to do all of the loop iterations that are sitting inside that simple little box. Okay? And let's suppose that box has dimensions x by y plus by z. Which entries of A, B, and C do I need? Well, this face is the A face, so I need all those entries of A. That's the B face. I need all those entries of B, and that's the C face, so I need all those entries of C. How many entries of A are there? Well, x times z. How many entries of B? Y times z. Entries of C, x times y. What's the volume of the box? It's x times y times z. So how do I get the volume of the box if I only know the areas, the faces? It's pretty simple. Just multiply them and take the square root, and I get x times y times z. Okay, that's a box. But what I need to prove my theorem is to say no matter what shape this is, and if I know the areas, how do I bound this quantity, the volume, as a function of the areas? So here's the general case. And this goes back to a classical theorem of math from 1949. So I can have any set of cubes that I want. There's the entries of C. I'll call that the C shadow, just project it up. There's the entries of B that I need, the B shadow, and there's the entries of A that I need. And so if there's a point here, ijk, then this is just ik, right? So just project it orthogonally. So here's the famous theorem from 1949. An upper bound on the volume here, the number of cubes, is just the product of the areas, take the square root. Here it's equal, but it's always an upper bound. And that's the intuition that we're going to use. And I'm not going to do the proof. It's a little bit, it's a couple pages of elementary stuff, but it's that's all we need. So let's go back. And so the number of loop iterations that I can do with m words of data, that's the number of cubes, is the area of those 3 shadows. And obviously, each shadow is at most m, right? I can have most m entries of A, m entries of B, and m entries of C. I'm not worrying about the constants right now, right? This is all big O kind of notation. And so that means I can do at most m to the 3 halves useful pieces of work given a cache of size m. So that means that I need to do m times n cubed divided by f, and that's where my n cubed over the square root of the cache size comes from. So that's the lower bound, and that's what you attained in homework 1. So it's the number of loop iterations divided by the square root of the cache size. Okay. So that's the lower bound, and the question is, why do we know that you attained that in homework 1? So again, let me just remind you of the answer to homework 1, and talk about why that hits this lower bound. So what I need to know is what's the largest number of inner loop iterations that I can do given m entries of A, B, and C. And so just to say that geometrically again, so what's the largest set of points in that cube, ijk's, that I can have given a bound in the number of of projections, the A face, B face, and C face? And just saying it one more time, what's the shape that I want? So for n body, it was a square. So now I want to know what's the largest 3D shape when I know that the 3 sides have bounded areas. What do you think? A cube, exactly. Your intuition is just fine, right? So so it's a cube, and its dimensions are square root of m by square root of m by square root of m, or a little bit smaller, so it all fits inside the cache. And that's exactly what your optimal algorithm for homework 1 kind of looks like. Obviously, you'll pick. There's a whole bunch of tuning. It won't be exactly the square root of m. It might be smaller a little bit, so everything fits and all of that. But this basically tells you what it looks like. So. Just to repeat what I said before, so this is the upper bound, the number of loop iterations divided by the square root of m. But the same reasoning tells us the answer for the parallel case. And we're going to have a whole lecture later on how to, what optimal parallel matrix multiply looks like. But now I can tell you what the lower bound is on the communication. So now what I want to do is bound how much data moves from one processor to another, because that's the expensive thing in a parallel computer. So it's going to be the same kind of reasoning. I have local memory on each processor. That's like the cache, so whatever the local DRAM is in each processor. And then the slow memory is everybody else's memory on all the other processors in the computer, right? So I want to minimize how much data moves between the processor I'm on and every other processor. So how do I do that? It's going to be the same formula, the number of loop iterations in the numerator divided by the square root of the memory in the denominator. So I have to figure out what those are. So what's the number of loop iterations that each processor is going to perform in parallel if I have p processors multiplying n by n matrices? I want it to be load balanced. Every processor is going to do an equal amount of work. So every processor is going to do n cubed divided by p loop iterations. It doesn't tell you which ones they are, just as long as it's load balanced, that's what it is. So what about the denominator? How do I pick m? Well, the simplest thing you could imagine is that I have one copy of every matrix spread out over the machine. Every processor gets one piece of it. And so I have 3 n by n matrices. Each processor gets one piece of it. And so m is 3n squared over p. Plug that in, so that's the numerator. Square root of that's the denominator. And I get n squared over the square root of the number of processors. And yes, there is an optimal algorithm that hits that. And we'll talk about that in a later lecture. Now, I was giving this lecture a few years ago, and I pointed out, and I'll do that here too, I pointed out to the students that this lower bound is true even if m is larger than this. That means even if I have more memory than one copy of all the data. So why would that be useful? It tells me that, in principle, if I could replicate the data, make more copies of it, I could make my lower bound get smaller. And in fact, there is an optimal algorithm that goes faster by replicating the data. And we've gotten like 10x speed ups on some parallel machines by doing that. And so the student thought that was a good idea, and he formed a startup, and it was called Nirvana, which was acquired by Intel a few years ago. He had a bunch of other good ideas too. So who knows what may come out of your class projects. Okay. So now let me remind you of 2 slides from Kathy Yellick's lecture before and tell you about a variation on it. that that may surprise you. So for your sequential optimal matrix multiply, one of the algorithms we pointed out that worked was called recursive matrix multiply. So in that case, if you want to multiply two n by n matrices, you break them up into smaller matrices of size n over 2 by n over 2, and then recursively do 8 smaller matrix multiplies. And then add them up, and that worked. And the idea was, eventually, as these matrices get smaller and smaller, they'll fit in the cache. And the algorithm, which just does all these things recursively, you don't need to know what the cache size is. And so that meant that, instead of having an algorithm which had to know how many layers of cache that you had and how big they all were, this just always worked. So this is very attractive. These algorithms are called cache oblivious. But if you keep doing recursive calls down to 1 by 1 matrices, then you get a lot of overhead for each floating point operation. So you need to stop the recursion a little early. So here's what the code looks like. And here are the formulas we wrote down, which are quite simple to solve. So what are the number of arithmetic operations to multiply n by n matrices? I did 8 problems of half the size, 8 times n over 2 problems of half the size, plus a bunch of additions. And if you solve that, you get the same number of multiplies and adds the classical algorithm does, because this is the classical algorithm, just doing things in a different order. And there's a similar recurrence for saying how much memory you move around. It looks almost the same. You count the number of words moved for problems of half the size, you do it 8 times, and then you have a whole bunch of adds. But now the base case, it doesn't go down to 1 by 1. Once the problem fits in fast memory, it stops. There's no more data movement, and so the base case is just a much larger matrix. So now, so this is just a review. And what I'd like to do is ask you, what do you think would happen if I could somehow do not 8 problems of half the size, but 7 problems of half the size? How would that improve things? So you won't get n cubed anymore. It's going to be n to a smaller exponent. And this is called Strawson's matrix multiply. And it was invented back in 1967. And it turns out that you can do these n by n matrix multiplies by 7 problems of half the size. And it's kind of magical. So what are the 7? Here they are. And so you have to take linear combinations of all these submatrices, multiply them, and then add them up so that all the extra terms cancel. And you end up with the right answer at the end. So I'm not, please don't try to do all the algebra in your head right now to confirm it. This works. So this is sort of surprising. It was a big surprise when this was published. And so what is the cost now? All right, I've changed the notation, sorry. So this used to be A on the previous slide, number of arithmetic operations. I'm only doing 7 problems of half the size, and then a bunch of additions. And instead of getting n cubed, n to the log base 2 of 3, I'm getting n to the log base 2 of 7, which is smaller, n to the 2.81. And so this algorithm actually beats classical matrix multiply once your matrix is large enough. The constants are bigger, but it has set world records on big parallel machines doing this. Again, you may not want to do recurrence all the way down to 1 by 1. You may want to stop early. But what's also interesting is that this hits a communication lower bound. People ask the question, we ask the question, okay, if I'm going to do this particular algorithm, but I can do the operations in any order that I like, just as the same for matrix multiply, can I prove a lower bound, and can I attain it? And the answer is yes, and it's almost the same formula. So the old formula was n cubed over the square root of m. All I'm going to do is change the 3 to log base 2 of 7. So the numerator goes from n cubed n to the 2.81. And this used to be 3 halves minus 1. Now it's log base 2 of 7 over 2 minus 1. So the communication has gone down asymptotically, and everything else has gone down asymptotically. So when this was published in 1967, it set off many decades of ongoing work where people have kept trying to make that exponent smaller. So let me just give you a little recent history. So for a long time, people worked on it, and then in 1987, somebody got the exponent down to 2.37 ... Okay, and that was a world record for a long time. Then in 2011, a postdoc here at Berkeley got it down from 37548 to 37293. So that was the first big improvement in 20 years. Okay, that was Virginia Williams, who's now faculty at MIT. And then in 2014, the new record got it down even a little bit smaller. All right, so maybe it's asymptoting out. Nobody knows right now. But the nice thing is that one of my colleagues in the math department had a PhD student who proved that all of these algorithms have a common communication lower bound. And it looks just like the one we had here, except log base 2 of 7 turns into whatever that magic exponent is, 2.37 dot, dot, dot. And that is the lower bound for doing any matrix multiply. And people have even asked, well, can I get down to n squared? And they formulated that as a rather complicated group theory problem, because all of these correspond to sort of certain kinds of group factorizations. And so you can read about that if you're interested. So you can actually show that they're all numerically stable. So in addition, because we care about getting the right answer as well as going fast, and so there are some numerical stability proofs that we do. And we showed that in principle, you can use this as a building block to do any linear algebra problem just as fast. So least squares problems, solving AX equal B, eigenvalues, and so forth. And some of these are realistic, some of them are just sort of big O kinds of things. Strawson is kind of the winner. All the other methods that people invented then, you would need galactically large values of n in order for it to actually pay off, because the constant hidden inside the big O is just kind of crazy. Okay, but anyway, a lot of people are still thinking about this. So now let me talk about arbitrary code that looks like nested loops accessing arrays and say, how do you do all this again? So here's what matrix multiply looked like. And here's my abstract model that I'm going to generalize to arbitrary code. So I'm going to iterate over some triples of integers, some, which is, a cube, but it doesn't have to be a cube. And all I need to know is that I'm accessing these locations, the subscripts of the 3 matrices. Okay, so that's all I needed to do the lower bound for matrix multiply. So here's a more general case. I can have as many nested loops as I like. They don't have to go from 1 to n. They can be over arbitrary subsets. I can have as many arrays as I like, as many lines of code as I like. And the subscripts can be arbitrary messy things, just I, j, linear combinations, whatever you like. So here's my abstract model of what that looks like. I'm iterating over some subset of k tuples of integers. And I just keep track of all those subscripts. And so I have a projection onto, for C, I'm going to call it a projection for A. I just keep a list of all those. And what I'd like is any code that looks like this, I want to have a communication lower bound and an optimal algorithm for any code that looks like that. Okay, so it covers all the things we've done so far and many, many others. So we can do that. So let me tell you what the result is without proving it. So given any program that looked like that, then there is a magic number, S sub HBL. HBL is the acronym of the names of 3 famous mathematicians, whose theory we're using. I'll tell you who they are. So that no matter how you reorganize that code, the number of words moved is lower bounded by the number of loop iterations, same as before, n cubed for matrix multiply, times your cache size to this magical exponent. And that magical exponent, it was 1/2 for matrix multiply, it was 1 for n body, but it could be anything depending on the structure of your code. So where does that magical exponent come from? You need to solve an LP, linear program. And HBL, I'll tell you in a moment who HBL were. So what I need to do is minimize this sum subject to a whole bunch of linear constraints where this linear constraint is defined by group theory. So there are all these different subgroups of ZK, and I have ranks of subgroups and so forth. Anyway, I can do more details if you're interested, but it's just a finite linear program and you can solve it. And that tells you the magical exponent. And I should say that the proof depends on a recent result in pure mathematics by my colleague Mike Christ in the math department, Terry Tao at UCLA. And here's where HBL comes from. This is a generalization of what's called the Holder-Braskamp leap inequality to abelian groups. And this is basically a generalization of every inequality you've ever learned in a math department. It includes Cauchy-Schwarz, Loomis-Whitney, everything, right? It's just the ultimate generalization of all these inequalities. Okay, so we know what the lower bound is. And then we proved there's always a way to tile the input space to attain that lower bound, no matter what your loop iterations look like. So it was, squares for n-body and cubes for, for matrix multiply, but it gets much more complicated if you have arbitrary nested loops. Now, we do have some assumptions, obviously. It's all big O kind of stuff, right? So that's how theory works. It depends on the loop dependencies. So I'm assuming I can reorganize my code in any order. And in matrix multiply, I'm just doing a bunch of sums, so I can do those in any order. But if I were to take Gaussian elimination and completely randomly do all the inner loop iterations, I wouldn't get the right answer, because I have dependencies. We can attain the lower bound for Gaussian elimination, but you have to be careful. And so the best case is to say there are no dependencies, or I'm just doing reductions. So as we'll see, convolutional neural nets are a good example of that. And I'm also going to assume that the loop bounds are large enough so that my optimal tiling fits. So suppose I wanted to do matrix times vector multiply. That's sort of a special case of matrix-matrix multiply. But my optimal tiling is a cube. And a cube does not fit inside a vector, right? It's too fat. And so I can't hit that lower bound for matrix vector multiply. I have to, I can't take advantage of the cache. There's no data reuse in matrix vector multiply. So since we realized that, we've asked ourselves, how do we extend this theory to cases where you have small nested loops? So let me tell you what the optimal answer is for convolutional neural nets. So let me express convolutional neural nets as a bunch of nested loops, and then apply the theory and I'll just tell you what the answer is. So what I do, I have an image which has a whole bunch of channels, a whole bunch of different colors, and each image has a height and a width. I also have a bunch of filters. And so a filter is a little, R by S, could be very, very narrow, and there's one for each channel. And I have K different filters. And what I'm going to do is take each of these filters and move it around inside here and take a convolution, take a dot product, of all these R times S times C values. And then, as I move them around, I'm going to get this output, right? So, and this is of depth K because I have K different filters. Okay, so that's the simplest way to describe what a convolutional neural net does. And of course, I usually don't have just one image. I have a whole bunch of images, so I could have B of those. But it's going to be the same set of filters for all of them, so that's my opportunity for reusing it. And I can easily express that as 7 nested loops. I'm going to loop over all of the filters, over the height and the width, over the size of of each filter, the number of channels, and the number of blocks. And the inner loop looks like this. I'm going to take the image, and I'm going to take the filter, shift the image around, apply it to the filter, and add it to the output. So this fits exactly what we were doing before. So actually, it's a little bit more complicated because this assumes I'm moving the filter around just by one step at each time. In general, it can move by a whole bunch of different steps. So this is what it looks like. Instead of moving the filter by one step each time, it's going to move by sigma W. So this is what the inner loop looks like. And what I'd like to do is have an optimal algorithm for implementing this. So what people do today is they run something called im2call, which just takes all of this and turns into matrix multiply. And then they just call the tuned matrix multiply that's available on every platform. So it turns out that we can, in theory, beat matrix multiply. So let me tell you what the lower bound is. And so remember, the numerator is going to have the number of loop iterations in it. And so there's the number of loop iterations. I just don't want to, it's the product of all those bounds. I'm going to call that capital N. M is my cache size. And because the answer now depends on the sizes, because if this is really small, like it's a 3x3 filter, then the optimal tiling may not fit. I may have a different optimal tiling for tiny little filters. So that is why our theory gets more complicated. And we've actually automated it with Mathematica, so that was important to do. So the answer is going to be the maximum of 5 different terms. And any one of these terms could be the max, depending on the sizes of all those bounds. So the first 3 terms are kind of obvious, because you have to write the output once, at least. You have to read the image at least once, and you have to read the filters in at least once. So the sizes of the input and the output are kind of natural lower bounds, but sometimes that's the biggest. The next of the one is if we just apply our theorem straightforwardly, it turns out it's the n-body problem. So it's not matrix multiply, it's really doing the n-body problem. And so I don't have m to the 1/2 in the denominator, I have m. So it's much, much better than matrix multiply, but that only applies if my filters are really big. So what happens in the usual case when the filters are not enormous? So here is, the most general lower bound. It looks like matrix multiply, but it's smaller by this funny factor. So the filter size divided by the shift size to the 1/2. So if that weren't here, this would be matrix multiplied, loop iterations divided by square root of m, but it's smaller by this factor. And as I said, we have Mathematica code that generates optimal tilings in all these cases, so it is attainable in theory. So it beats matrix multiply by that factor. This factor applies in the common case when the data doesn't fit in the cache, but one filter does. And that's because the tile is too big to fit in the bounds. And as I said, my student Grace wrote Mathematica code, so this is proof by computer that every one of these cases is attainable, and there are like 100 different cases that are generated automatically depending on this. Okay, so I'm going to close with one more piece of eye candy to show you how these tilings get more complicated for more complicated loop nests. So this is a variation on n-body. This used to be a sub I and b sub j. Now I'm just going to make the subscript a little bit more complicated, and we're going to see what the optimal tilings look like. The theory is the same. It says the best I can do if I have a cache of size 10 is read in 5 entries of A, 5 entries of B, and do 25 things. What's the optimal shape of the tile? It turns out to be a parallelogram. And that's not a problem. We can tile with that, okay? So now, let me make it just a little bit more complicated, probably not realistic, but just to give you a sense of what the optimal tilings look like. So now, as I said, I can have these arbitrary kind of linear combinations. Again, I'm not telling you this is realistic, but the theory deals with it. So again, I want to read in 5 entries of A, 5 entries of B, and do 25 pieces of work. What do you think the optimal tile is going to look like? There it is. So it's still a parallelogram, but now it's sort of spread out a little bit. And I'm reading in these 5 entries of A, those 5 entries of B, and I can do that tile. And then I can shift it around and tile the plane, but I'm missing some things, right? I mean, all these little black dots aren't covered by that tile. Well, the good news is the theory says that all you have to do is take all these tiles, shift them up by 1. You can do another 25 each that you didn't do before. Shift it up by 1, shift it up by 1, shift it up by 1, and then you've covered them all. So this involves a lot of computational group theory that all of this is derived automatically. So I'm not sure this is practical, but it works. So that's a good place to stop. And are there any questions? Okay. See you next time.